Welcome to Problems. And the week three is all about tracking and dynamic stability. And the most of the question, if you see how week three is like, so the question are involved a mix of stability and the dynamics of the manipulator and stability. But if you have, I will solve some problems. Yeah. If you have any problem, please do unmute yourself and ask any specific. Most of this problem, I think, if you see, those are related to the lectures only. These equations also, these equations are quite the same as what professor has already taught you. So, but I don't think if these questions can be asked in the same question can be asked in the final exam. So what in this week, what I did was like I've make some two or three new questions so that get to know how to solve different how to solve problem which is apart from lectures. So yeah, so let's start the today's session. So the first question is based on dynamics, then we will move to stability. These are the two main area where most of the questions are from, specifically for this week. uh, Start the session. If you have any problem or any question, please feel to unmute yourself or you can write it in the chat box. Start the problem. So here you see RP manipulator, which is a Revolut plus planar robot. So it's a 2 degree of freedom manipulator here, and you need to find out the equation of motions. I mean, dynamic equation. Basically, to dynamic equation means what do you mean by dynamic equation? Like basically torque equations or the force equation. So like so you see there are two joints, right? There is this prismatic joints and there's this fluid joint. So these are two different links, and in order to move these links, we need some kind of a torque or a force. So those dynamic equations, those Newton equation, the laws of equation like force, all, all those terms needs to be calculated. So for this, we are using again the Lagrangian-Euler theorem. Uh, so there are two links. So we need to first think about. We need to find out first kinetic energy and potential energy, right? And this is the first link. And in this link, it's rotating at an angle theta 1, and it has a center of mass located at this L1. Okay, and I think it also have inertia, so I think I missed that part. So there will be inertia I1, I2. So I1, I2 are the inertias. So this I1, I2 are the inertias along this along its center of mass. Okay, not with respect to this point. So along the center of mass of this whereas for I2, this is the center of mass of spider link. So first of all, we need to find the kinetic energy. How to find the kinetic energy? So in order to find the kinetic energy, we need to know velocities, right? So let's just say this is theta angle, right? Let's say how to find the kinetic. So for kinetic energy, we need to know the velocity, right? So let's say V1, thing like first we need to know the position and then position of the center of mass. And if we know the position and center of mass, we can differentiate it and get the velocities, right? Something like L1 sine theta, right? Uh, this is sorry, this is x coordinate, and this is y coordinate. 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 And will be y. Sorry, this is x. Y is L1 sine theta, and x is L cos theta. And when you differentiate this thing, you'll get something like y dot and x dot, which is theta dot, right? Similarly, you will get the same thing, and when you find out the velocity, it is something like x dot square plus y dot square, right? And when you do that, you will get something like L1 theta 1 dot, right? This is what you will get for the link one, and this is about the link one. And so here the interesting thing is link two basically. So if you see how to find out the link two, so previously you are used to two revolute joint, right? But here it's different. So here we have some planar joint also, right? So how to find out the velocity? How to find those velocity? So the center of mass here. Okay, how to find the velocity? So again, you need to do something the same, right? Find out the position vector, which is basically P2 cos the one, and the thing x x2, right? This is y2. Y2 will be sine the one. And when you differentiate these things, so please do consider that in this case the L1 is constant, but here the D2 is changing, right? Because it's a prismatic joint, right? When you differentiate this thing, so there will be some kind of a product rule which applies here. So it will be D2 dot cos theta minus D2 sine theta, the one, and theta dot will be something. This will be x2 dot, and again it will be same for something like, I mean, you can do this thing part, okay? So when you do this, you just need to square and take a root in order to get the resultant velocity, right? This will be v2, and when you do this, you will get something like dot square plus something like one square. So this is what you will get when you do the simplification, right? Basically, it's so this is the same here. I mean, you see, this is the tangential velocity. dt d2, basically you have read this, right? It will be like d2 theta 1 dot, and this is something like a radial velocity, right. So here they have followed something like here they have not the transform. Here they have followed something like a Cartesian coordinates. So previously you have gone uh, to the professor's lecture. If you've seen, those are using Cartesian coordinate, where here they are using polar coordinates. This is radial component, this is tangential component. Basically, when you do the same thing, you will get the same thing. Okay, this is the velocity you will get, and after velocity, you need to find out the kinetic energy. So kinetic energy consists of both terms, consists of linear velocity, linear kinetic energy, and this is uh, this is translational kinetic energy, and this is, I think, a rotational kinetic energy. I1 is the moment of inertia about its center of mass. This is with respect to the first link, and when you do for the second link, it will be again v2 squares to this. Here if you see v2 square, they have just squared and added this radial and tangential term, right? And if you do the same with Cartesian coordinate, you will get the same answer. And again, moment of inertia will remain the same, right? Kinetic energy is the crux of the whole Lagrangian island. Mostly you get potential energy easily. Potential energy is nothing actually. So potential energy is basically, suppose if this is something like a zero potential energy, how much potential energy each will have, like mgl sine theta, right? This you can get easily. This will be m2d one, right? So potential energy you can get, but the crux is the kinetic energy. So you need to be careful when you are calculating kinetic energy. And again, you find out the Lagrangian. You just need to subtract it. If you have subtracted it, you need to use those Lagrangian error formula. So there will be two equations. There are two links. So 2 degree of freedom system. So you have a theta one direction, which is the first link. So in this term, the generalized coordinate, which is actually that q will be replaced by theta one, right? And it will something like this. And in order to move that link, we need some kind of a torque, right? And when you do this thing, you will get something like that. If you partially differentiate theta one dot. So please uh, do this calculation. Okay, so please try to solve some example problems, right? Because it looks easy, but when you do those partial differentiation, you will find some mistakes. Okay, please be careful. So like they have partially differentiated with respect to theta one dot, right? I'll just give you how they have. So this is our L. It partially differentiate with respect to one theta one dot. Okay, theta one dot. So it will be that v2 theta one, right? And this all term will be zero when you partial differentiate this whole thing be zero because there is no theta one dot. Okay? Please remember they are doing partial differentiation. Okay, not the simple differentiation. So this is what you will get. And when you differentiate with t, again there is. So please do remember there is this d2 term, d2 dt, yeah, d of 2 square term. There are two variables. Okay, so please do apply that product. Okay, and again for the second link, you need to replace q with d2. Okay, and here it will be force, not torque. Okay, because that's a prismatic joint. You need apply a force in order to move that link. So when you do this partial differentiation, this is what you will get. And yeah, and when you do this differentiation again, will again get something. Yeah, what you will get when you partially. So when you differentiate this thing with et, you get something like this. So this is so writing this whole term in a some kind of a matrix form. So please do the differentiation, and when you find you get this, this is what you will get, the 1 by d2. And then this is a mass inertia matrix, and this is we call as a pyrolysis or a centrifugal term. Basically, here you will get a centrifugal term. Here you will get both term, and this is the gravity term. How you this is how you will solve some kind of a. This is how you will get the dynamics equation of a particular. How you like to solve. So this is regarding the dynamics problem. If you have any doubt, please do ask me. And I think most of these cases, if you see these equations, I think they wanted to calculate moment of inertia, so you can easily get this equation. Because all this equation, if you go to professor's lecture, I think the lecture two, if you remember, all this moment of inertia equations have already been given by. Please go through this lecture and please have a look. Okay, so like this moment of inertia equation. They've already given this moment of inertia formula. Plus, please don't remember this because I don't think they will ask the same question. Might be because I'm not setting up the question paper. Can be either, but please don't remember. You can prove this thing. Okay. Please remember the steps, okay, how to reach there. I think I will move on to the next question. Okay, so this question is regarding the Lyapunov function. So this is a kind of a different question here. So let's read the question first. So the following is a suitable Lyapunov function candidate to assess the stability. So these are the different Lyapunov candidate which is given by the variable v, and it is without a control input. So this is basically your equation, and since the right hand side is 0, which means that we are not applying any torque, any so without a control input of equilibrium of a non-inverted pendulum, non-inverted point mass pendulum. So there is something like a point mass pendulum, and which can go from like minus 90 to 90 degrees. So this is, it can go, so whose domain already given to, this can go from here to here. Okay, measured from the vertical. Equation of non-linear dynamic of such pendulum is given. So this equation is already given to you, where L is the length and G is the gravitational. So you need to tell me from this option which of the Lyapunov function is the stable Lyapunov function. Which of this Lyapunov function is a stable function, right? For that, you need to, how you will approach this problem. You need to uh, check each option one by one. From that only you can get it. Okay, so there is no such formula. So for that, so if you have some Lyapunov function, you need to first check if it's a positive definite or not. And for stability, so like positive definite, it should be v should be greater than equal to 0, right? When x is not equal to, this is the positive definite, and v is equal to 0 when x is 0. The condition for v to be positive definite, which means function is eligible. So the, if this function satisfies, this means that the v is a Lyapunov function, right? So stability should be something like that. It's v dot be less than 0. Yeah, it should be less than 0. And so please do remember this condition. Okay, these conditions are important. So v dot is less than 0. uh yeah, so v dot is less than 0. uh, Dot is less than 0, and dot is less than 0 or all x not equal to, if it's negative definite is opposite of that. And if it's 0 or x equal, this is a negative definite condition. This condition is called uh, condition is called asymptotically stable. Okay, and then there is other condition, which is when you see e dot can be less than 0, or it can be equal to 0 for all, for all x. Okay, for all x. So it can be x and y. So it can be anything. This condition is called a stable condition. This is asymptotically stable. This is stable condition. Please do remember this difference between asymptotically stable and stable. Okay, I will solve this problem so that example it get clear. So let's just solve the first problem. So here v is given here, which is k1 theta 1 square, k2 theta dot square. And if you have this, so please use this equation, right? There are two states, which is theta 1, theta and theta dot. Okay, please do remember how to use, like, this is e is k1 theta dot square and k2 theta dot square. This is greater, this will be always greater than 0, because these are square term, right? And this is, and when this is not equal to 0, when this is will be 0 when theta and theta dot are 0. Okay, this first condition satisfied, which is a positive definite. then we need to check if it is stable or not. For that, we need to differentiate things. Okay. Then if you differentiate it, it will be 2k1 theta dot and 2k2 theta dot and theta double dot. Okay. So theta double dot, you can use this equation JL sine theta, right? Minus JL sine theta. That's what they did. They have taken this minus E by L sine theta, and they have converted this k2 to some k2 dash, and this is how you will get it, and this is thing you will get. Okay. And you need to see if it is less than 0 or not. If it is not, then it is not stable, or then it is unstable. So if you see this, there's this k1 theta 1, there's this k2 theta sine theta, and then theta. So you see there are lot of theta terms are there. Okay. So you can't comment on it. Basically, it can be negative, it can be positive. Okay, let's say for sine theta equal to 0, it will be 0, which is kind of a great. But let's say sine theta equal to 90 degree, which is pi by 2. Sine pi by 2, it will be 0 here, but yeah, sine pi by 2 is 1 here, and here it will be pi by 2. You don't know k2, but you know theta 2, and k1 and k2. It depends. So you don't know what is k1 and k2. So you can't really say about it. First option is wrong here. Coming to the second option. So in the second option, the second option is a half theta dot square plus g by L 1 minus cos theta, right? So please use this domain. Okay. So what is the domain? Domain is this theta. Okay. So let's say in this domain, if it is greater than 0 or not, let's see. So theta dot square, it will be all, you can take any theta, it will be 0 only, right? But if you see this term, so cos thetas, right? So when you put theta from minus 90 to 90 degree, what, how the cos theta will be? Cos theta will be, the maximum it can go is 1, and it is theta is 0. And in that case, it will be 0, but this doesn't mean that it will be 0. Okay? But when you say pi by 2, then it will be 0, then again it will be positive. So V will remain always positive. V is a positive definite matrix. First condition satisfied. Coming to the second condition, is it stable or not? Again, you differentiate stuff, and you will get theta and theta double dot, and this is g by L sine theta dot. Yeah, theta dot. And you replace this theta double dot with this equation gl by sine minus gl by sine theta, and again you do stuff, and this is what you will get, which is 0 basically. Okay. This 0 means v dot is always 0. Okay, there is no such equation is there. It means that it is 0 for all theta and theta 1 dot, right? Means that it will be stable. Okay, it will be stable because it is always 0. I know it is not less than 0. Less than 0 is not a necessary condition. Should be, it can be 0 also, but in this case it is always 0. So here in this case, B is right. And take B. Coming to second condition, which is C, which is V equal to half theta dot square. Okay. And yeah, in this case, let's see, you have theta and theta double dot. Theta double dot, you replace it with something like this, and you can't really comment actually. Then you can't really. Theta dot can be anything, sine theta, because sine theta is a cyclic term, can be negative, or it can be positive. This minus 100 to 90. So it can be positive or negative, so you can't really comment on it. So C is also wrong. And coming to D option, G by L sine theta plus half theta square. So please, first we need to see if it is LPDF. LPDF is PDF, which is positive definite matrix. Okay. We need to first check if it is for this domain, if it is always greater than 0 or not. Okay. So for theta dot square, whatever you will put, it will be positive only. Let's see for this one. Can't really say because sine theta can be negative or positive in this domain. So you can't really say. Here the option answer will be B here. So that B is your answer. And coming, so there is one more question on system stability. If you have any question, please do ask me. Check chat and see. So I have two more questions, then we will wrap this up. So there is this again a question where we need to see there are equilibrium. So there are different equilibrium states has been given to you. Yeah. So these are the different equilibrium state. So for which of this system x is zero, then equilibrium state stable in the sense of Lipnov. So we need to tell which of them is stable. Okay. So they have already written stable, which means that it can be stable or it can be asymptotically stable. Nothing matter. It needs to be stable. Okay. So it can be both, can be any of them. Okay. So let's start the question. So we need again we need to approach this problem one by one only. Okay. So we need to check each option one by one and then have to can come at we can come at a conclusion. So let's first, what is the question? So for this system, so we need to in order to check any Lipnov stability function. So there are two states has been given it to you has been given to you. Is there are two states so that how it look like. So basically, this is something like the x. What is it? Here x dot is something like so x dot x is kind of a vector which of all x like in this in the first case. Previous case, it was like theta and theta dot, right? This case, it is something like x and y. There are two different variables. These do approach. So this kind of a like a 2 degree of freedom system. Yes, it is 1 degree of freedom system where it is theta and theta naught, where here there are it is x and y. And so how to check if the system is stable or not? First, we need to come up with a Lipnov function. So first, we need to see what is the Lipnov function. So like we have to come up with such a function which is whose who's always greater than zero, who's positive definite, right? So please do always take an energy function. Basically, it's like a velocity kind of a thing we are doing. Half x square plus half y square. Whatever y or x value should be, it will be greater than zero. And when x and y is zero, then only this p will be zero. So first we need to take the Lipnov function, which we have taken it here. And then in order to check the stability, we need to differentiate stuff. And if we do that, then there is x dot, y dot. And yeah, and using the using this autonomous equation, this an equation, x dot is minus y. Just put it minus y, and this is will get so it is zero. So v dot is zero, some kind of a positive semi-definite or a negative semi-definite. It is a stable function. Okay. If it is, let's say, I mean, the other option. So let's see the second option, which is so instead of x dot, we are replacing h dot with minus x plus y, and y dot we are replacing with minus 2x minus y. When you do the simplification, you will get something like this. Is minus 1 by 2 x of square plus y of. So if you see here, this will be always less than equal to 0. Okay. except the case where x and y equal to 0. Basically, it's a condition of asymptotically stable condition. So A and B option both are right. Coming to C option, x0, y0. So when you put x dot, y dot 0, the v dot will be 0, which is some kind of a stability. So it is stable function. So C is also right. Coming to D, if you put x dot equal to y, then v dot will be something. Into the simplification, it will look like 2xy. 2xy can't really say. Let's say if you take x equal to positive, y equal to negative, it will be negative. Take x equal to positive, and if you take y equal to positive, then it is a positive. So you don't really know always for x and y is enough. So here in this case, you need to see for both x and y. Okay, so both x and y. In that condition which you have, so the previous condition you need to check for all theta and theta dot. Okay, not for only theta. So here the states are two, which is x and y. Okay, so it is not always less than equal to 0. Okay, so you can't really say if it is less than 0 or not. So D option is wrong because it's not less than equal to 0. You can't really say. So answer here is A, B, and C. Okay. And if you have any question, please do ask. And this is the last question. This is regarding Lipnov stability one. I know sometimes, I mean, this Lipnov stability can be difficult, mostly due to its uh, due to its definition. Because okay, when to take not, when to take, how to take those Lipnov functions, why we are doing it, why not like to, but this is how they have it, right? This is how you need to solve if a system is stable or not. Why the stability is important? Because if we can somehow take some kind of a, so like in this case, if you, so in usual case, you want to control the pendulum, and most of the equations are non-linear equations, and those equations are difficult to control. Those problems are difficult to control. That's why this Lyapunov function. Basically, there are other approaches also to find stability. There are eigenvalue approach. There are other thing called Raoult's criteria. But this is one of the most universally accepted criteria, which you, this stability criteria will help you when you when you want to make some kind of a robot. Is very complex. Okay. Coming to this big question, the last question. So a small box moves on a track as shown in the figure, and classify with justification each of the equilibrium point A, B, C. There are equilibrium points, so there is only A, B, no D here. Okay, is a D. So we need to see that each point, if you see, so like this track, so this small box is moving, right? And we need to see if it is being stable at A, B, or C or not, or right. So we need to tell if it is stable, asymptotically stable, or there is something called attractive and unstable class. So these, please don't remember this. Please don't. Please, attractive part. Uh, uh, for now, please note stable class using Lyapunov epsilon and delta naught. So if you remember that epsilon and delta naught definition, we are using this definition to see if it is stable or not. Okay. Assume static and kinetic friction coefficient are the same if the question asks to consider. So first of all, please let's brush up what the definition is all about. So to know, if you know from the previous class that There's something called x dot as some, not mine, x minus like x minus x e, something like that is less than equal to like that, right? There was the definition, but please consider that these point A, B, and C are at the equilibrium point is zero. Okay, so if you change this, this is how it look like. So let's say this is a small box, and let's say the state of the box is x and x dot. So we need to consider the position and the velocity of a box. Okay, there are two states, and let's say we have drawn that on a Cartesian or on a phase plot. Okay, which is x1 and x2. X2 is basically x1 dot, and let's see what's the definition say. So let's say this. Let's say if it is at time equal to zero, time equal to zero, uh, time equal to zero. Let's say your object is something like your object or your box is something here, and if you have some small perturbation, so small perturbation means there's some small velocity or some small position you have given here basically, and it should be less than, it should be, let's say, a delta. Let's say if you have a body here, okay, and at time equal to zero you are just small, just give a small push, not, it's a small push, it's not a excitation, but it's a small push. Okay, that push is basically x is equal to, let's say, some small value, say and x dot is equal, and so which is what delta denotes here. Okay, when you do the x the square and something like it, and you wanted to see if it is stable or not. For that, when you say system is stable, when this after time equal to, let's say, infinity, say after that push you yeah, after that push, like so after that small push, you have taken you have just allowed the object or allowed the box to move on its own. Okay, leave it on its, and you see at time equal to infinity how the box is. Okay, so if the box is something in the small range, let's say if you have given a small push, it has reached something here, something like a delta, a bigger epsilon circle, right? Bigger epsilon circle in this phasor plot. Okay, which is something like an epsilon, right? So if it is remain in this circle, which means that it is stable. Okay, and the other condition is like asymptotically stable. So if the when we say if the system is unstable, asymptotically stable, when we say at time t equal to zero, time t equal to infinity, that same body has started from here, but it has reached to zero, thing like that. Okay. So what we did here is, like, if you have this ball, you have just disturbed it for a small point of view. So let's, if you have disturbed something like here, okay, but due to its stability, it comes back to its position, which is zero position. This is what asymptotically stable look like. Okay. So now let's approach this problem. There are 3 points A, B, C. Let's see one by one. So let's say for point A, right? This is point A, right? And if you have given small perturbation, right, like this, you give a small perturbation like this, hopefully it will go something like here. Okay, but it won't like go to here because that's a very small, the delta is very small. basically it will remain here. Okay, it will remain in this epsilon only, delta. So the first condition is uh, stable condition. A is a stable condition when there is a friction. Okay, okay, when there is a friction, then we say that the condition is stable. Which condition? This condition. Because if you give something like there is a friction, due to friction, it will stop here. Okay, and yeah, so this is basically the formula which you should take. Okay, so the first case is friction is absent. Okay, no matter how small, when you move something like that, you give something. If you, let's say, if there is friction, it will stop something like here. But if, let's say, if there is no friction, okay, if you give a small push, it will go and it will move up. Will like let's say this is epsilon naught, it will move away from this boundary. Okay, then it will become unstable. So when friction is present, then it is stable. When friction is absent, it will sorry, when friction is present, it is stable. But when friction is absent, it will move like here, which is outside the boundary of epsilon naught. Okay, now let's consider C point here. So C point is something like, so let's say C point. So C point is at the edge of this mountain. Okay, if you give a small push, it will be something like here or here. Okay, let's say this is epsilon. Sorry, this is eta and this is epsilon. It's far away from that. Okay, so even if friction is present or absent, it will fall from this peak. Okay, so there is no opposing force. Okay, so the C point, which is at the peak, is unstable because it is going outside the boundary. Whereas if you consider B point, which is like at this depth, you give something like a push here. So let's consider step by step. Okay. Let's say if you are given a friction, if this case the friction is absent here, right? The friction is absent. What it means is that you have given a small push, which is delta. It will move something like a delta here, delta, and it will come back due to some kind of a gravity is there. So it will something like oscillate when there is no friction. Okay, when there is no friction, it will oscillate and it will remain. This is because it is coming back, always coming back, right? Delta is, let's say this is delta. No, sorry, this is epsilon naught. And the epsilon naught will remain as same as delta here because it will always come back. Whereas in another condition where when there is a friction, if you have given a small push, it will go something like this. It will decay. That oscillation will decay and ultimately it will come to rest. Okay. So at time equal to infinity, that box will come to its same position, which is basically x equal to 0 position. So in that case, if friction is present, then it is called asymptotically stable. Okay. If you have any doubt, please do ask me. And one of the most important point which I was so so the this is what they have done here, right? If the friction is present, they have like they have used the velocity, and this velocity will be equal to mu mgx. I think this you already have done it. X max is they have calculated it, and they have used this equation, and they have small enough thing, and this is like no should. So if the friction is present, this is how they have treated the problem. They have calculated all those equation. I mean, you don't need to go into this depth. They won't even ask you. They just need to know. They just need to see like if you can recognize each point from your eyes if it is asymptotically stable or A, B, C, you can see. Okay, so please do consider the friction thing. Okay, friction is present, the whole condition will change accordingly. I think yeah, I think that's it. think yeah, it's 7:47. I think stop here. And I think most of this question, I think you can easily solve this equation because most of this the torque equation like this one, this torque equation has uh, already been uh, already been proved by a professor. Please do look into the notes, and using those formula you can solve this kind of a question. I haven't prepared anything because I mean that will be like spoon feeding you because most of these equations have already been solved. I've made some new questions so that can get to know like how to solve a question which is different from which is different from what I think. If you have any questions, ask me and section. If you have any guys, please do ask me if you have any questions. So for now, I think I will stop here. Uh, yeah, I think so is about yeah, artificial network. And week four is let's see assignment look like controls have introduced whole thing. That looks interesting. I think there are only 10 questions, so please do look into the videos, okay? And and I think there's something called Q&A. If you have any specific question regarding any lectures or any something like assignment, you can ask in question for. I will not reply in this, but there are other TAs who will reply. These two platform. Okay, so I will stop here.